the same time as our knowledge of the Earth has been revolutionized by new discoveries, so new discoveries are greatly expanding our knowledge of the other planets in our solar system. The Viking landings on Mars are an example of the kind of information, or the kind of projects which are yielding information that is greatly increasing our understanding of how our Earth fits in with the other members of our solar system. Flights are also on the way to the outer planets of our solar system, much, much farther away than Mars, to planets like Jupiter and Saturn. And very rapidly, we're beginning to see how the Earth fits into the solar system of which it's a part. It's a branch of geology which illustrates once again how the science borders on other sciences. We've already seen how it borders on biology, for example. Geology also has links to astronomy. And it's geologists who've been concerned with the interpretation of the data from other planets, because it's geologists, of course, who look at the rocks of this planet. It's a unit that you will find, I think, fascinating. Putting the Earth in perspective is only possible once you have some idea of what the processes and the geology of the Earth is like. The geology of the other planets is sometimes very, very different. And with that earthly knowledge as a reference point, then it becomes quite exciting to look at the other planets. The first part of the hour is the Planet of Man film, The Cosmic Connection, and then another half hour of the planets of our solar system, all putting the Earth in perspective.
I often think, as I sit on the deck of this Hong Kong junk, especially at night time, that it'd be wonderful to see a really large shooting star. Some people do see them from time to time, you know, and the larger ones often produce a stone that falls to Earth. That's to say, a meteorite. Many meteorites have been collected now and studied, and they've told us quite a bit about other parts of the solar system. And recently, in the last few years, astronauts have visited the Moon, and satellites have flown past Mercury and Mars and other planets fairly close by and given us good photographs of these. So that we're finding out a lot about other heavenly bodies, and this tells us in turn a good deal about the Earth. So this program is devoted to what we know about meteorites and other planets.
In 1928, a remote region of Siberia was visited by a scientific expedition. Their aim, to study the circumstances surrounding a strange event observed and heard by thousands. Eyewitnesses told of a blinding flash of light, ear-splitting explosions, violent gusts of air. "20 years after the event, L.A. Kulik led an expedition to the Tunguska River region of the USSR to find the location of history's greatest suspected impact from outer space. At the site, Kulik found devastation. Trees snapped like twigs, their tops scorched and burned, their trunks spread out fan-like from the center. The forest, dead 20 years, lay rotting at its roots. Kulik believed the depressions he saw in the swamp were craters, formed by meteorite impacts. But he found no meteorites. All the excavations and drillings were in vain. It's now believed that the Tunguska devastation was caused by the fall of some other cosmic body, perhaps the head of a comet, but not a meteorite. When the solar system was formed nearly 4.5 billion years ago, some fragments were not incorporated into any of the planets. These remaining smaller bodies, called asteroids, are concentrated in a belt between Mars and Jupiter, known as the asteroid belt. Some asteroids, not in the belt, fly through space to strike other planets. Those which have not yet struck a planet are called meteoroids. As meteoroids fall into the atmosphere, they become heated and vaporized by friction and appear as luminous streaks, meteors. Here at the Springhill Meteor Observatory of the National Research Council, observers plot the magnitude and direction of their meteor sightings. Millions enter the Earth's atmosphere daily. All but a few, however, burn up. Those that survive the journey to land on the Earth are called meteorites. Most are very small. The possibility of a large meteorite hitting the Earth is very remote. But time is long. Harvey Nininger, a pioneer in the study of meteorites. His persistent research and fieldwork moved the study of meteorites from a naturalist's hobby to a scientific discipline.
I knew there were asteroids that were circulating between Mars and Jupiter. And there must be, from what I could learn, there must be millions of them. And I was sure that occasionally they must have bumped into the Earth, and that in doing so, they would become a force in geology. Now, that I'm not so much interested in the 8 or 15 or 20 that have been seen to cross the orbit of the Earth in the last few decades. What I'm interested in is what has gone on before this. If this has happened in 30 or 40 years, what's happened in 30 or 40 million years? Would there be 18 or 20 million of them that have crossed the orbit of the Earth? And did they all miss the Earth? While we were talking, suddenly the sky just split wide open. A fireball like which I've never seen before or since came down, and I was so full of the subject I had been thinking the last few weeks, I reached in my pocket and got hold of a crayon, and I marked a place on the sidewalk. He said, "What are you doing?" I said, I'm going to try to find that fellow. And he laughed. He said, you think something came to Earth? Yes, I think so. I feel sure of it. Well, where? Well, I said, you saw where it disappeared, didn't you? I said, somewhere out in that direction, about 150 miles from here. And then he laughed again. He said, I know now you're kidding. I said, no, I'm serious.
Until the 19th century, few in the Western world believed stones fell from the sky. In 1894, the Aniket meteorite was brought from Greenland to New York City. 34 tons of it, the largest displayed meteorite in the world. After millions of years in space, this iron-nickel body fell to Earth. Called the Willamette iron, few meteorites are as impressive as this 14-ton specimen.
Are you going up?
In 1947, another impact in Siberia was certainly the result of a huge meteorite. A scientific expedition to the Sokotoline Mountains found hundreds of small craters formed by meteorite fragments. Pieces of iron-nickel body were found 26 feet below the surface. This fragment weighed 770 pounds. This larger one weighed 1,650 pounds. Although not always easy to recognize, the surface of the Earth bears many structures that appear to be impact craters. The energy released by impact of a large meteorite collision staggers the imagination. Tremendous shock waves surge out from the impact. These shock waves compress material to high densities and distort the rock layers. At the turn of the century, a mining engineer, Barringer, identified Meteor Crater in Arizona as the impact site of a giant iron-nickel meteorite. Dave Rodey of the U.S. Geological Survey explains what he and astrogeologist William McCauley have learned about Meteor Crater.
Of 20,000 years ago, in this particular area, there was a large iron-nickel body traveling approximately 10 kilometers per second. It impacted the area and created an enormous shock wave into the ground as well as into the meteorite itself. The meteorite, because of the shock wave passing through it, broke into many, many fragments. It was on the order of 60,000 plus tons in size or in weight and on the order of about 80 feet in diameter. The meteorite itself, as it was broken up, was injected actually into the crater walls, with much of it also being thrown outside of the crater. Consequently, we have no large single mass remaining. The final crater was approximately 4,100 feet across and over 600, nearly 700 feet in depth, with structural deformation below that another 1,000 feet.
Specific characteristics are looked for in identifying a meteorite crater.
Well, probably the most important single criteria that was used at Meteor Crater is the fact that it is actually a big bowl-shaped crater. The more specific elements have been the general deformation that you see in the rim of the crater, the large amount of material that's been thrown out of the crater, and the nature of the topography or the rolling hills that you see around the crater itself.
The Sudbury Basin in the Canadian Shield is an elliptical structure 26 miles long and 15 miles across. Earth scientists have often debated the basin's origin. But the presence of rock formations called Shattercones indicates the basin was a probable meteorite impact site. Shattercones are associated with meteorite impacts. They can be found in Meteor Crater in Arizona, or associated with nuclear blast sites, areas of high energy explosion. The immensity of the shock required to produce these Shattercones suggests that the Sudbury Basin had its beginning as the location of a meteorite impact. The Canadian Shield is a chronicle of ancient meteorite craters. Manicouagan crater near Sept-Îles in the province of Quebec. Its beginnings go back 200 million years. In the same province, the new Quebec crater has seen the advance and retreat of more than one ice age. The Brent crater in Algonquin Park houses 2 lakes. Sediments date its creation 400 million years ago. These pockmarks have survived in the Canadian Shield because the hard granite is very resistant to erosion. Arizona's Meteor Crater is, geologically speaking, very young. Yet, within a few million years, erosion will have made it difficult. Volcanoes, a host of features similar to the Earth's, but on a much grander scale. Nix Olympica.
This is the largest known volcano in the solar system. It is something on the order of 600 kilometers in diameter from this side here to the far side down here, with a large central crater or caldera, which is on the order of about 100 kilometers across. The distance across this feature is about half the size of the state of California. It would stretch roughly from San Francisco on this side to Los Angeles down here. In addition to such spectacular finds as this, we discovered enormous canyon systems that girdle parts of the equatorial belt on Mars. And we see here a mosaic of part of this canyon system, along with its gullies along the walls of the canyons. We see the south wall of the canyon here, the north wall up in here. We see a subsidiary canyon or a parallel canyon over in here. And then we see tributaries to this enormous depression in the crust of Mars in this region here. This one is of particular interest because it gives us some idea of the scale of the type of feature we're looking at. This particular tributary to the main Mars Canyon system is as large as the Grand Canyon system of Arizona. And the total length of the Mars Canyon system is approximately that of the width of the United States itself.
Evidence for the cosmic connection among planets is strong. Bombardment with interplanetary matter is common to them all. It's in the preservation of impact evidence that they differ. On the Earth, erosional, volcanic, and tectonic activity have obscured most of the early history of meteorite bombardment. On Mars, surface processes have also been active, but not sufficient to completely destroy the impact craters. But the Moon and Mercury wear their scars in vivid splendor. With little surface activity in their cosmetic history, these planets testify to the severity of their bombardment. Until planetary exploration began, Earth was our only geological laboratory, and the satellite camera attests to her beauty.
Perhaps one of the most important aspects of our exploration of the Moon and of Mars and the other planets is that the knowledge gained about these planets and the early history of their surfaces will apply to a better understanding of our own planet and how its surface has gotten to be the way it now is. Much of the early history of the Earth is no longer accessible to us because of the dynamic character of the Earth's crust. And it's through the exploration and the sampling and the photography of bodies such as Mars and the Moon, and also some of the other bodies such as Mercury, that will provide us with a better and more complete understanding of the early history of our own Earth.
Geologists have been looking at the Earth in a scientific way for about 200 years now. And especially after we have now landed on the Moon and begun to explore it, and after spacecraft have orbited other planets, Venus, and now even landed on Mars, many geologists have begun to wonder just how the Earth compares with other planets in our solar system, and perhaps even with planets in other solar systems, if there are any. The film you've just seen, The Cosmic Connection, gives some indication of the connections in the history of the planets in our solar system. But it didn't give very many answers, and the reason for that is that we just don't have very many answers at the moment. It's still very much speculation. Nevertheless, after 3 months of looking at the Earth in this course, I think it is worthwhile speculating a little and trying to put the Earth in perspective as far as we know it. Getting back, if you like, from the trees and having a look at the forest. For 1,000 years, astronomers followed the dogma which held that the Earth was at the center of the heavens. But in 1543, the Polish astronomer Copernicus published his conclusion that the Earth and other planets were in fact in orbit around the Sun. He was supported by other astronomers, including Galileo, who was one of the first to work with a telescope in the early 17th century. A space vehicle traveling at 18,000 miles per hour would take 46 years to cross our solar system. And even light traveling at 186,000 miles per second would take 11 hours. But seen in perspective, our solar system is simply one of 100 billion within the galaxy we call the Milky Way. And here the dimensions of space become almost impossible to grasp. Distances are so tremendous that even the speed of light seems slow. To cross the Milky Way, it takes light 100,000 years. And our galaxy is but one of uncounted millions of other galaxies in the known universe. With radio telescopes, we can detect galaxies so far away that it would take light 26 billion years to reach us. Galaxies, not planets or even suns, are the main units of the universe. And they've been studied extensively by astronomers ever since they were recognized for what they were. And recently, some effort has been put into computer studies of hypothetical galaxies in an attempt to understand how real galaxies develop and behave. Data on the size of and rotation of any number of stars up to 1 million can be fed into computers. From the data, the computer constructs a variety of artificial galaxies, speeding up the real rotation of once in a few 100 million years to a matter of seconds. A comparison with real galaxies can be used to judge the success of the computer. If you look up at the night sky, many of the so-called stars that you can see are in fact galaxies, great swirling clusters of stars. And if you were to go to the Mount Palomar telescope, the largest telescope on Earth, you would be able to see about 2 billion galaxies. The light from the farthest one having left there about 4.5 billion years ago, just at the time that the Earth was formed. Now, despite their appearance as great clusters of stars, galaxies are in fact mostly space. If you were to take our own solar system and convert it to the size of a dime, a quick calculation will show that the nearest star would be about 200 feet away, and between them would just be space. The powerhouses of solar systems and of galaxies, and in fact of the universe, are the suns. Our sun, like other stars, is an immense sphere of hot hydrogen gas, about 865,000 miles in diameter. It contains over 99% of all the material in our solar system. The temperature in the center probably reaches 10 million degrees. The surface, at about 6,000 degrees, constantly surges into immense prominences and flares, reaching thousands of miles into space. The Earth on this scale would be about the size of the tiny dot at the center of the screen. The prominences are made up of electrically charged gases, which carry an electric current and become trapped in the sun's magnetic field, often cascading back into the surface in a spectacular fashion. The violent surface activity releases bursts of electrified atomic particles, which reinforce the general outward flow of particles from the sun called the solar wind. This gas-like wind bombards the planets and distorts the magnetic field of those which have one. A bow wave even builds up in front of the magnetic field, which acts as a shield. The same solar wind causes the tail of comets to shine by energizing the gases in the tail. At the same time, it drives the tail away from the sun. This is Halley's comet, photographed in 1910. When the atomic particles of the solar wind arrive in the vicinity of the Earth, traveling at 700 miles per second, one of the most spectacular results are auroral displays. The atomic particles stream in at the magnetic poles and they collide with the molecules of gas in our own atmosphere. The pattern of the lines of magnetic force of the magnetic field are best seen in the coronal type of auroral display. But you shouldn't think that the solar wind is only reaching the Earth when we see auroral displays. If you were able at any instant to take a cubic centimeter of the Earth's atmosphere, and a cubic centimeter is about a sugar cube size, you would find in it approximately 10 atomic particles of the solar wind, mostly protons and electrons. And that solar wind and those particles are a reflection of the thermonuclear processes which are going on inside the sun and which keep it hot. The sun is not burning material in the same way as we burn material on Earth. It's keeping hot and supplying us with energy through a process which converts hydrogen to helium in a manner akin to that used in hydrogen bombs. And in the centers of some stars, only to a very limited extent in the center of our own sun, which is relatively cool, in the center of some stars, the process goes farther, and the nuclei of other elements, aluminum and iron and carbon and nitrogen and so forth, are also formed by a continuation of the same thermonuclear process. So stars and our sun supply energy. They are also the factories, if you like, for the nuclei of new elements. They're also the center of gravitational attraction for planets. That is to say, we know our own sun as a center of gravitational attraction for our own solar system, and we assume it's probably the same for the other stars that we can see. We can't see their planets because the light reflected from the surface of the planets, if they're there, is too dull for us to see. But we have detected the wobble of some suns as they rotate, and that's interpreted to mean that their gravity is being affected by the attraction of planets which are circulating around them. So our sun then is the center of a solar system of 9 planets. And on this scale, if this is the sun, the Earth, instead of being this size and here, ought to be the size of a small pea about 80 feet away. And the farthest planet from the sun, Pluto, should be about half a mile away and the size of a small pinhead. And remember what I said about galaxies being space? The nearest star in our galaxy on that scale would be, well, we're in Sudbury in northern Ontario. Would it perhaps be in the prairies? No, it would be even farther than that. The nearest star on this scale would be somewhere in the Pacific off the coast of Vancouver. Let's have a look at some of the characteristics of the planets of our Sun. The planets are regularly spaced in an almost flat disk, and all orbit in an anti-clockwise direction around the Sun. The inner four, including Earth, are heavy and rocky. Where the fifth should be, there's only a band of debris, the asteroid belt, beyond which are the enormous outer four, the mysterious gas giants, and tiny Pluto. Jupiter, the largest of the four, has a dense and turbulent 800-mile thick atmosphere of hydrogen and ammonia crystals. Ringed Saturn, nearly 900 million miles from the Sun, is the next. In 1979, Pioneer 11, launched in 1973, will visit this spectacular planet and might even photograph sunrise over Saturn, if it survives the rigorous journey. Third of the gas giants, Uranus, rotates on its side, and it and its moons circle the Sun like a fallen gyroscope. And finally, Neptune, nearly 3 billion miles from the Sun, the smallest of the typical outer planets. The Pioneer 10 and 11 spacecraft, launched in 1972 and 73, were faster than any previous craft, traveling at 1 million miles per day and passing the Moon in just 11 hours, but still taking 2 years to reach Jupiter. The craft each carried about 65 pounds of scientific instruments to measure such things as ultraviolet and infrared radiation, magnetic fields, and the number of particles which struck the craft, all powered by less electricity than needed for a 25-watt light bulb. A radio dish transmitted data back to Earth and also received command signals from Earth. Approaching Jupiter, the spacecraft took the first close-up pictures of Jupiter's clouds of ammonia crystals suspended in gaseous hydrogen. The clouds form the light zones, which are higher and colder than the dark bands. The dark spot on this photograph is the shadow of one of Jupiter's moons, Io. The famous red spot seems to be a hurricane-like storm, which has persisted for over 300 years. It's about 25,000 miles across, and 3 Earths would not cover it. At its closest, the Pioneer 10 spacecraft approached to within 81,000 miles of the cloud tops. The spacecraft detected high-intensity bolts of atomic particles apparently wobbling up and down and somehow related to the strong magnetic field which surrounds the planet up to 4 million miles away. Computers had to be used to produce the spectacular pictures of Jupiter. Because of its rapid rotation, once every 10 hours, and because so much of it is liquid, Jupiter is quite flattened at the poles. One puzzle which still remains is the nature of the chemical which gives the dark, apparently lower belts of gas, their distinctive yellow-brown color. Pioneer 10's successor, Pioneer 11, will travel beyond Jupiter, and if all goes well, will reach Saturn in late 1979. If it returns pictures, we will learn much more about Saturn's glittering 40,000-mile broad rings. Someday, a landing vehicle may even descend on Io, one of Jupiter's moons, at first discovered by Galileo. If it lands as the Sun strikes Io, after being hidden by Jupiter, it may be able to record one of the most dramatic sights in the solar system. During its hours in the frigid darkness, Io's thin atmosphere seems to snow out onto the barren, possibly salt and sulfur-covered surface. When the Sun appears, it flashes from solid ice directly back into gas in the space of just a few moments. Of the outer planets, only Pluto, the outermost of the planets, is an oddball. Pluto is apparently rocky, rather like Io, that moon of Jupiter. And in fact, Pluto is possibly an escaped moon of Neptune, in fact, and not really an original planet comparable with the others in the solar system at all. The remaining outer planets, the 4 remainder, are all gassy. The bulk of their makeup is gassy hydrogen or ammonia or ice. They're quite different from the planet that we live on, quite different from the inner planets. Jupiter, in fact, contains the bulk of the mass of the solar system outside the sun. And in many ways, one can look at the solar system as a two-body system, the sun and Jupiter. So enormous is Jupiter. Saturn, one of the most beautiful of the planets because of its rings that you saw, is a very light planet. In fact, if one could find an ocean big enough, one could put Saturn in it and it would float. The other two, Neptune and Uranus, are, as you saw, much smaller, not at all comparable to Jupiter and Saturn in size. Let's have a look at the structure of those very different gassy outer planets. Jupiter probably has a small rocky core, and outside that is highly compressed hydrogen, highly compressed because of the enormous pressure it's under. And then finally the outer shell of Jupiter is liquid hydrogen. And above that is the atmosphere of Jupiter, formed probably of several shells. At first, water in the form of droplets, and then ice crystals. And then the shell succeeding that water shell is a compound of ammonia and sulfur, ammonium hydrosulfide, in fact. And then the next shell is formed of ammonia crystals, frozen ammonia. And then the highest shell is gassy hydrogen, still gassy despite being extremely cold. Saturn is rather similar to Jupiter, also with a rocky core, and then a layer of ice, or a shell of ice. And following that, again, highly compressed hydrogen, and then liquid hydrogen. Uranus is a much smaller planet than Jupiter or Saturn. It also, though, has a rocky core, quite big in proportion for Uranus, and then highly compressed hydrogen, and finally, like the others, liquid hydrogen again. Now, the upper layers of the atmosphere are very cold on the outer planets, probably somewhere in the region of -150, -200 degrees. And in the end, only hydrogen is still gassy at those temperatures. The inner planets contrast very markedly with those gassy outer planets. Let's have a look at their characteristics. Mercury is the closest of the inner planets to the sun. Cratered and rocky like the moon, Mercury has a harsh surface environment with a midday surface temperature of about 700 degrees. It's too small to hold an atmosphere, and its history of bombardment seems closely dissimilar to that of our own moon. Venus, in size and mass, is similar to the Earth, but puzzlingly it spins on its axis in a direction opposite to the other planets. It has a thick atmosphere, mostly of carbon dioxide, which has made observation of Venus difficult, but some of that atmosphere may be sulfuric acid. It too has a high surface temperature, about 400 degrees. Mars has always been intriguing because of its supposed seasonal changes. It's some 50 million miles farther from the sun than the Earth, and is a cold rather than a hot planet. The inner planets then are rocky planets with rocky surfaces, just like our own. And one of those inner planets which has attracted particular attention recently because of the Viking landings is Mars. Mars seems to have quite a red surface with strewn boulders and showing the effects of wind. Another feature which has been seen on Mars is stratification, or it seems to be stratification, rather like we find in sedimentary rocks on the Earth. These may be layers of volcanic ash, or they may reflect the freezing of water beneath the surface, rather like permafrost. Another feature which is well known on Mars is evidence of wind. These are thought to be dunes, wind-blown dunes, that compare very well with those that we find in deserts on the Earth. And a final feature, which Mars has become notorious for, is evidence of water at one stage in the life of the planet. These canyons and valleys look as though they were quite certainly cut by water. So the inner planets then are a very distinctive group. And even our own planet is one of the most distinctive of them. A very blue, watery, cloudy planet, as many of us know very well. The composition of the inner planets is also quite distinct from that of the outer planets. No gas, just rock and iron. The structure and composition of the Earth, you should remember. A core, an inner core, we think of liquid iron nickel, and then an outer core of solid iron nickel, and finally a mantle of iron magnesium silicates surrounded by a very thin crust. Mars compares quite closely with the Earth, we think, also with a core of iron nickel and then a mantle of iron magnesium silicates, a rocky mantle, and probably also a crust. Mercury has a much larger core, we think, than the Earth and Mars. Although it's a very small planet, it's a very heavy and dense one. And the mantle of Mercury is relatively thin compared with that of the Earth. And finally, Venus, again with an iron-nickel core, about the same proportion as the Earth, in fact. In fact, Venus is very much in size and makeup a sister planet of the Earth. It's only the atmosphere which differs. The mantle of rocky silicates is just about the same thickness as the Earth's, we believe. So the composition of the inner planets contrasts markedly with the composition of the outer planets. How can we explain that difference in composition, those groupings of rocky and groupings of gassy planets, when we look at the origin of the solar system? Well, the current explanation for the origin of the solar system is entitled the cold accretion theory, which you've already met in the program, The Inner Limit. It's thought that the solar system condensed out of a rotating gas and dust cloud. The first thing that happened in that rotating cloud was that material began to gather towards the center because of the gravitational attraction at the center of that spinning cloud. The material also tended to gather in a disk around that growing center. An artist's impression of that stage gives you a more dramatic picture than this diagram. The sun-to-be is at the center of this whirling disk. Before the sun became the body that we know it today, sufficient material had to be drawn into the center of the whirling disk for nuclear reactions to begin. Gravitational energy of the material drawn to the center had to be converted to heat. When that happened, then the sun began to shine. And at the same time, protoplanets were beginning to be built up in the whirling disk around the sun. Those protoplanets were aggregations of material which had stuck together. Pieces of rock, pieces of dust, pieces of ice, and so forth, that had stuck together. Those bodies grew to be the protoplanets, the mini-planets which preceded our own planets. And the next stage involves the collision of those protoplanets, those mini-planets, and their welding together to form the planets that we know today. An artist's impression of that stage gives you a more dramatic picture than in that diagram. So the disk of protoplanets whirling around the sun, naturally you would expect those protoplanets to be revolving in the same direction. And that's the reason why the planets all orbit in the same direction around the sun. You would also expect that the accumulations that finally formed the planets would form at regular intervals in the whirling disk. That's why the spacing of the planets is regular. And because of the heat generated at the center of the whirling disk by the sun, you would expect the gases to be in the outer part of the disk. Therefore, the outer planets are the gassy planets. Now, some material was left around in that whirling disk that never became incorporated into planets. Those are the meteorites. This rare footage of a meteorite in flight was taken quite by chance in Alberta in 1972. We'll show it to you twice since it's quite short. The meteorite only broke up a little and seemed to have skipped through the atmosphere and returned to space, which was probably just as well, since it was calculated to be about 150 feet across and would have caused quite some damage if it had come to Earth. Most meteorites, however, break up when they reach the Earth's atmosphere, like this one, which broke into 35 fragments. One of the most spectacular results of the accumulation of meteoritic debris of this kind in the higher levels of the Earth's atmosphere are noctilucent clouds, here shining in reflected sunlight very brightly above the Arctic Ocean. Comets are also part of the solar system. They orbit very, very far out beyond the planets and only very occasionally cross orbits of planets such as our own. Meteoritic dust falls on the Earth at the rate of about 100 tons per day. So comets and meteorites are very much part of our solar system. Some of you may have wondered about life on other planets. Well, it's a good bet that since we know 100 billion galaxies, that on planets revolving around the stars of some of those galaxies, there are intelligent species. In fact, it's even a good bet that around the stars of our own galaxy are planets which have on them intelligent life. It's a good bet that some of those intelligent species, perhaps one per year, become as technologically capable as we are. It'll be great fun one of these days to have an intergalactic geology conference